Hello, Philippe. So we are here today because our analysis of our new Cosmos database of climate studies shows that you are the most highly cited climate scientist in the world. Congratulations. So can we begin, please, with you explaining in very simple terms what your research focuses on, so we can all better understand why it's had such a huge impact?
Yeah, thanks, Leo, for the visit. And so my research is about carbon cycle, and why we care about the carbon cycle, because human activities emit a lot of CO2 in the atmosphere. It's the main driving force of climate warming, but we live in a very, very lucky planet, because half of these human emissions are absorbed by natural reservoirs, forests and oceans. And all my work has been to try to understand which region is taking carbon or may sometimes release carbon, what are the processes, is it because plants are growing better or oceans are dissolving more carbon, and how can we anticipate what will happen for the future. And for that, of course, we need numerical models, so-called Earth system models.
There's some quite technical terms in your science. You've got terms like atmospheric inversion and flux, and they seem to be quite central to your research. What do these terms mean, and why is it so important for us to understand and monitor them?
Yeah, you have two ways to kind of elucidate. It's a very difficult problem, because in the planet you have biology, you have physics, chemistry, and they're all intricate together. We know that ecosystems are terribly complex, and they are very heterogeneous. Like one forest here can take carbon, you go 1 kilometer away, this other one can lose carbon. So how to get carbon budget is a difficult problem, because you cannot measure every part of the world to get flux data. So there are two approaches. Either you try to get some local flux measurement, like acupuncture, you get some points here and there, and then you try to fill the gaps to produce a nice map. And this is called the bottom-up approach. It's powerful, but of course, in entire regions where there is no data, like in Africa or the Southern Ocean, you make big extrapolation errors. And I've been working on another approach called the atmospheric inversion approach. The idea is that the atmosphere is like a huge flux chamber. It receives everything. And in fact, at the end of the year, if you look at the growth of atmospheric CO2 at Mauna Loa, a single station, you know how much carbon has stayed in the atmosphere, everything including emissions and removals. If you have a bit more station than Mauna Loa, let's say a station in the north, a station in the south, etc., you see that they are not all the same. You have subtle atmospheric concentration gradients, which reflect two things: the atmospheric mixing and the fact that you have different regional fluxes. So the art of atmospheric inversion, that's why it's called an inversion problem, is to take the concentration gradient in the atmosphere to simulate the effect of atmospheric mixing and to reveal the effect of fluxes. So it provides a map of fluxes which is fully consistent with the nice small observed atmospheric gradients between sites. It has some advantage in the sense that it is complete. It's a mass balance approach. So there is no risk of missing any flux in big regions. But the problem is that it's mathematically a nil-constraint problem. We have very, very few stations or observations compared to the density of fluxes we would like to find. So we still need to help a bit the mathematical system by giving it some constraints so that the solution doesn't look crazy. So there are still a lot of assumptions, but the beauty of this approach is that it's based on physical mass balance. And if it is complete, you don't omit some fluxes. And that's a very important point.
So you've talked about these fluxes and the way that the planets, the atmospheric mix and things. So you've got the natural processes, but obviously there's a human process now. Can you just explain what the negative impacts are on that balance, that cycle that humans are causing to?
Yes, so humans, they release CO2, and once CO2 is in the air, it's not going to get out soon. It takes centuries, millennia before it's cleaned up. And this extra CO2, which is loaded in the atmosphere, it has two effects. One is a good one, the other is a bad one. The good one is called the CO2 fertilization. The fact that when you elevate CO2, you create an imbalance between the atmosphere and the ocean wants to take more. A little bit similar for the plants. Plants take more photosynthesis, they are more active when there is more CO2 in the air. Everything else okay, like water, nutrients, good temperature. So if there was only a CO2 fertilization effect, we would be happy because basically emissions could be removed. The problem is that there is a kind of malefic effect of CO2, is that it also warms the climate, and this climate warming has very bad consequences, negatively affected carbon uptake. So we live in a world where there is a fight between the good guys, CO2 fertilization, and the bad guys, climate change impacting carbon sinks. So far, we still have a carbon sink, so the good guys have been beating the bad guys, but in the future, maybe the bad guys will take over, like permafrost carbon release, and they will turn our planet into a net source of CO2. So that's a big risk. Huh?
So yeah, I wanted to ask you about that. What concerns do you have kind of into the future or now even about the ongoing ability of the land and the oceans to take up carbon, balance? You know, are there concerns there about whether that, you talked about fertilization and the oceans absorbing plants, taking some of that CO2, but does that balance go on forever, or do you already have concerns?
Yeah, I'm very concerned because we have been trying to simulate for like IPCC Earth system model gradual changes. So there is a slow rise of CO2, the trees take more carbon. There is a rise of temperature, a little bit more extremes, and sometimes the plants and the oceans are affected. But what we are seeing more and more is abrupt changes. Like you have a hot summer in 2023 in Canada, and 11% of the boreal forest is burnt and releasing CO2. We have a massive drought in the Amazon, and trees can die in the lapse of 1 or 2 years. We have heat waves in Siberia, and we see that all this permafrost frozen ground is collapsing in 1 year. So all those abrupt change processes, when you measure them locally, you see very big carbon losses. And the big problem is that in the field, we see that they are very dangerous, but in the IPCC models, they don't exist. Most of the IPCC models which have been used to predict the future carbon sinks, they don't simulate tree mortality from drought. So when there is a drought, there is a little bit less carbon uptake by photosynthesis. The year after, everybody is doing well. In the reality, when you have a drought, you kill all the trees and you can perhaps replace your forest by another system. So models have been kind of adjusted to look for carbon gains, but they have not been developed enough to look for carbon loss processes. And the fact that we have this asymmetry of knowledge is a big problem, because you could argue that we are perhaps over-optimistic by underestimating or not looking at the carbon loss processes. Huh?
Mm-hmm. So in terms of that asymmetry and problems, you know, in terms of understanding this, what in your view is causing the roughly 1 gigaton imbalance in the annual global carbon budget, which, as I understand it, I think you've tried to investigate, but do you want to explain that a little bit?
Yeah, we have an imbalance. So basically, the imbalance reflects the state of the knowledge. In the way Pierre Friedlichstein and we do the budget is that we know from atmospheric data what should be the magnitude of the planetary sinks in the ocean and on the land just by mass balance. You remove from fossil emission the observed atmospheric growth rate. And then we use ocean simulators and land carbon simulators, and we try to produce a bottom-up estimation. We check, like your bank account, and there is an imbalance. Mm-hmm. So it's a problem, because a large imbalance means that we don't capture something.
Do you know what's causing that imbalance?
So that's, I think it's a very important scientific question. I think the question should be more, what are the regions that are contributing a lot to the imbalance? It's not like the culprit is the ocean or the culprit is the land, but is it because we don't have the right processes for the tropics, or because we are missing high latitude permafrost feedbacks? And what we tend to see is that the imbalance becomes larger when you have extreme climate events. Like when you have a big El Nino, like the last one in 2015 and the recent one in 2023-24, you see that all the models that had on average a small imbalance, suddenly during that year, they don't understand something because they don't get the right balance, which tells us that there is something missing in these models about the response of land, maybe ocean, to climate extremes. That's something to worry about because we have a lot of climate extremes. We know that the models have missing processes, like currently, none of the budget models is simulating the boreal fires. You ask them, make a prediction for the Canadian fire in 23. We are talking about a big anomaly, half a gigaton, and the models will say there is nothing. So we know that there are pathological problems. They combine because some errors can be positive or negative, but we have hints that the imbalance is not zero because models don't simulate the response to extremes. And it rings a bell for the future because if we don't capture extremes are basically natural experiments that can inform you about what could happen in the future. If you don't get this right, it means that your future projections could also have problems. Huh?
So just to put this in context for our Carbon Brief audience, so a 1 gigaton imbalance, that compares to about human emissions are what, 40 gigatons a year roughly?
That's maybe about half of China or the entire EU emission.
So it's significant.
It's significant, yeah. Okay. It's quite significant. Of course, the models have some tunings. So they don't want to produce a stupid result, like 5 times more carbon sink in the land than what is conventionally accepted. So generally speaking, modelers, to participate to the budget, they can adjust a few parameters to match the average carbon sink. So their average imbalance is never very big. It's not 1, it's 0.1. But one particular year, like last year, you have a big El Niño, and you have an imbalance of 1, which is revealed because the models do not simulate well the impact of extremes on the carbon cycle.
Mm-hmm. What is your view on CDR, carbon dioxide removal? Are you concerned that negative emissions technologies are too sort of baked in to emission scenarios being used to inform policymakers? Is there too much focus and hope placed on things like nature-based solutions and BECCS, bioenergy, and carbon capture and storage?
Well, of course, I'm not a very big fan, I must say, of CDR because there is clearly this moral hazard that if you just say, oh, this is the economic calculation of the IPCC and we can make 1.5 degree, quote, provided that we get enough CDR, people will understand that we can make 1.5 degree, and they will not necessarily understand that CDR is something which does not exist at scale today. It costs a lot, and we have a lot of scientific uncertainties about the permanence of CDR. It's well known that if you plant a forest, sooner or later the carbon may disappear. So on the one hand, we are getting desperate because we passed the 1.5 degree. We are heading to maybe surpass the 2 degree warming. So everything that could reduce carbon dioxide looks like something that has to be studied. But today it doesn't exist at scale. It causes, let's say, hazards in terms of generations because you are going to ask your sons and grandsons to clean the problem, which is not obvious. It has some technological barriers which are very strong, and also something which is maybe sometimes not seen with CDR. It has also some equity between the north and the south, because the big options for CDR are in the tropical countries. They can still replant a lot of forest, but they have not contributed too much of the current historical CO2 emissions. So basically, rich countries or big emitters are going to ask countries from the south, can you do CDR for us? And that's a typical problem of climate justice that will have to be sorted out if we really want to move CDR at scale.
So you mentioned that we're kind of past 1.5, which, you know, I guess if you're assuming overshoot scenarios which have huge assumptions around carbon dioxide removal.
Yeah.
So your concern is that we're already basically breaching 1.5, the Paris Agreement. We're heading towards 2 pretty fast. And if we go beyond those, and at the end of the century we want to come back down to those temperatures, as some of the modelling is trying to assume and investigate, the carbon dioxide removal is obviously essential to bring it back down.
The problem...
and as you say, there's a lot of not just assumptions, but problems that quickly
there are two problems with the CDR. The problem is that the more you let things go and emit, the more you have to clean. And since it's not easy to clean up carbon, otherwise we would have done it already, the economic, technical feasibility becomes smaller and smaller. Basically, maybe we could restore, let's say, terrestrial carbon stocks by, let's say, 1 time the Amazon. Suppose we plant all the forests in the good areas. But if we have to pack away on land 10 times the Amazon carbon, where is the land? We cannot do that. So the more we continue unattended, the more the CDR becomes something that may help to fix things, but it won't bring us back to degree. Huh?
So you are concerned that today's policymakers maybe have a signal that, this is tomorrow's problem. Next generation,
right.
The next generation can deal with the implications of CDR, but it allows today's policymakers to maybe feel a bit better about some of the choices.
Right, because for me, if you start to produce scenario with CDR options, the first part of the message is that we could do 2 degrees with CDR, will be very well understood by politicians and the governments. But the second big question is, can we really do this CDR and can we do the investment? And this is not done. So that's a big problem, of course, for this.
Mm-hmm. In recent years, there seems to have been an increasing policy focus on the short-term impact of methane emissions. Is this sensible, or are there risks to this approach where policymakers begin to focus on methane maybe more than carbon? I don't know.
Yeah, let's say you can see that as a good thing or a bad thing. The good thing about methane is that it's a very strong warmer. It warms the climate more strongly than CO2, and it has a very short lifetime. So if you press on the button to reduce methane emissions, in principle you could cool the climate. So this is fantastic. However, it has not happened yet. The Glasgow Pledge was supposed to bring down anthropogenic methane emissions by many countries by minus 30% in 2030. All the atmospheric data we have show that fossil and agricultural emissions have stayed constant or even gone up. Then there is a risk of, it's a bit like the CDR, that governments will say, okay, CO2, it's too costly, we won't manage. So, like CDR, let's try to promise very big methane emissions reductions. So there is a risk that there is a shift in the priorities and in the discourse that everybody can agree to reduce methane emissions. But, of course, CO2 stays in the atmosphere. So even if we manage to do something for methane emissions, we still have to address the problem of CO2. So the same kind of hazard about delayed action than we have for CDR. We jump on methane, it's low-hanging fruit. We make big declarations, and we delay the necessary action on CO2 emissions.
Mm-hmm. You've studied proxy data a lot, so looking at ways to analyze former past climates on the planet to help inform our understanding of today's and future climates. And what, in your view, are the remaining knowledge gaps that remain about the planet's past climates? And do you think we'll discover new ways to fill in those kind of data gaps around this?
Yeah, well, I've not doing paleoscience since a long time. I did that for my PhD. Of course, at the time, these ice core data were incredible because they gave us a global temperature and global CO2. And we found that they were, of course, very tightly associated with each other. One very interesting way to look at these paleo records over like last million years or even more is to understand what is a kind of love story between CO2 and climate. In other words, what is the climate sensitivity? So if you increase CO2 by 100 ppm from the observation, so everything included, ice sheet changes, vegetation, migrations, erosion, how much is the climate warming? And that's a very good benchmark. And of course, James Hansen has been using this brilliant idea to compare this kind of empirical estimation of very long time scale climate sensitivity with what is projected for the future by climate models.
What is your view on climate sensitivity? What is the range that you think, and has that view changed over time? And if so, in which direction?
Well, being a carbon cycle person, I prefer to speak about the so-called TCRE, you know, the kind of response of climate to emissions. I'm following as an outsider the literature on climate sensitivity. I've seen that in the last IPCC you have like two modes in the distribution, some very high sensitive model and some very low ones. So I wouldn't say, you know, which one is better or worse, but it's interesting that now when model gets more complex, in a probabilistic sense, they give you worlds where the climate sensitivity could be much higher than, you know, any previous model generation. And I think it also tells us something that in adding, in principle, new and more realistic processes in the models, more validation and so on, we don't shift the distribution towards lower climate sensitivity, but we shift the probability of higher climate sensitivities to increase.
You did your postdoc in the early 1990s at NOAA in Boulder, Colorado. What has been your reaction to the Trump administration's recent attacks on climate science, namely its desire to basically defund and destroy research institutions in the US focused on climate change?
Yeah, it has been very appalling because somehow the US community was leading, you know, a lot of this climate science, including incredible observations, like long-term carbon dioxide observations. Honestly, I would never have thought that it would come that hard, that quick. When I was discussing with climate colleagues after Trump was elected, before he went to the White House, they said, well, we had plus 10%, 15% budget increase with the previous administration. With Trump, we'll get minus 15%, and we'll remain stable. But in fact, the change is happening at a rate that nobody had anticipated. The communication battle was lost, clearly, because we thought after the success of the communication for the last IPCC report that the entire society would be completely convinced of the, you know, the importance and the urgency of climate change, but the discourse has changed. You have all these people who just say it's hoax, and because it's hoax, I'm going to defend it. So I'm very appalled by the rate of change of events. And of course, you know, when you look at this, you say, well, what will happen next in my little country, you know? Right now it's okay, but maybe in 5 years we have like a French Trump, and we will all be in the same situation. And that's really, like in the movie, Don't Look It Up, it's exactly what they had in the movie is happening. Yeah? So it's a very serious problem.
You've spent time in China working as a scientist. How do you compare your experiences of working here in France, in the US, in China? Obviously, three quite different, you know, situations in which to operate as a climate researcher and scientist. How do you compare those three?
Yeah, well, it was not at the same time. When I was in the US during my postdoc, it was an incredible place to work because the environment was very open. You could discuss with a lot of, you know, very experienced colleagues, and they would share their ideas and listen to you as a young scientist, which at the time did not quite exist in France. So this culture of you know, openness and discussion, I think it was, I learned a lot from it in the US. Of course, we took a lot of it in France and Europe, and we went from like pyramidal systems to more network of scientists. And having worked in China, I have been completely impressed by the ability of Chinese scientists to learn about things. When I started to work with them, I had the impression that I had a big amount of knowledge and that I was explaining them how to do things. They were, of course, working very, very hard, but it would take 20 years It didn't take 20 years. It took 5 years to, let's say, reach exactly the same level. And now, of course, they are ahead of things because of two things. In general, people work very hard. They have a very strong work ethics. And of course, in the end, it's also the amount of effort you put into research that delivers. The community has learned how to communicate. Before, for instance, they were in China less able to write high-profile papers because it doesn't require just scientific technical skills, but narrative and communication skills. Because the way you turn a result to a Nature paper is basically, it's like a journalist. You have to be a good storyteller. Mm-hmm. And the Chinese community, they were fronting this barrier of Nature, but they have passed it. Now they are extremely good at having high impact paper because of the storytelling, which is of course a very big component of these papers. And also, I have the impression that in China, being a scientist in the society is something that is good. You have a good salary, a good social status, a good respect, and a good career prospect. In Europe, it's a bit more like you are marginal, you accept to have lower salaries against more freedom, and the consideration for what you do in the society is not that high. So the shift in values has also shifted very strongly in China.
Because of that, do you anticipate in the next 5-10 years just Chinese climate research to just be on the ascendant? And do you think it could come to almost dominate climate research in the next decade or so, if you see some of the trends happening in the US and maybe even in Europe around the funding and focus on climate research?
Yeah, I think if you make a, best scenario, this will happen even soon. Maybe even now it's already the case. Of course, you have some geopolitical situations, and maybe there will be a downplay of climate in China. But right now, even for very fundamental aspects, I think Chinese science community will, of course, dominate everything we do because. They have invested a lot in big experimental facilities, and experiments are extremely important in advanced models, theoretical models. Now AI is helping our field a lot, and they have also captured how AI could be harnessed to improve climate models, accelerate climate science. Maybe the only weakness of the huge and diverse community in China is that there is not yet a culture of open data sharing, right, in particular for satellite data. Like NASA has been putting all the NASA satellite data open, and it's millions of papers. ESA in Europe was lagging behind. They launched satellite, but you couldn't find the ESA data. And now, with a program called the Climate Change Initiative, in fact, the best data center for permafrost, sea surface temperature, they are in Europe, Copernicus and ESA. China has an incredible satellite program, like Gaofen, it's an incredible set of satellites, but still, you don't have a data portal where you can find all this data for the science community. And this is still, the next step is to understand that, let's say, being a dominant player in the world in science, you have more to gain if you share data and information rather than if you keep it and think that you are more competitive because you have, let's say, private information. And so that will be the challenge.
Which leads me on to my next question, which is a hypothetical question, which is, say today I have a check or I have in cash 100 million euros, and I don't, but I give it to you. What research priorities would you spend that 100 million euros on? Would you expand the network of land-based monitors that you've been involved in, or would you rather spend it on a brand new satellite, for example, to capture new data, or maybe something else altogether?
Yeah, well, you have to put your money in the right place because, let's say, for 10 million euros, you can do major progress in improving climate models. For 100 million euros, you can launch half of a satellite. So you have to consider your assets. There are different possibilities. I would put maybe 1/3 or half of it to produce extremely accurate digital Earth for the current carbon cycle, like tree level, or current level, ocean current level maps, empirical maps.
So what kind of resolution do you see?
Well, typically for land, you can go to 5-meter resolution. For ocean, maybe 1 kilometer, by combining AI, Earth observation, and physical process models to have basically a reference digital twin of the current carbon cycle. That would be, of course, a priority. I would spend 25% with a very good postdoc to try to add the missing carbon loss processes that we were talking about in the carbon models to reduce the imbalance precisely in a coordinated way. And we know that we need more observations, so we need both more bottom-up, like flux towers, and atmospheric observations. But we know now that the atmosphere is a very important reservoir. Its atmospheric inversions are complete. And we have found a way to measure atmospheric CO2 at a cheap cost with upward-looking remote sensing instrument. Before, a station was costing like 1 or 2 million euro, and now it's 200,000 euro or pounds. You can buy almost an autonomous greenhouse gas sensing station. Mm-hmm. And in Africa, there is no station. In South America, there is 2. In Southeast Asia, there is 1. So having 20 stations in Africa and similar numbers in the tropics, I think would be a terrific, like fast progress in 5 years to reduce the uncertainty on the budget from atmospheric observations.
Do you think, is someone going to fund that? Is that actively being argued right now, or is that just remaining a big kind of data gap now in those key regions?
Well, everybody agrees that there is a gap. You have 2 ways to fill the gap. Either you go through the UN and the WMO, and they will have a strategic plan and a lot of committees. But in the end, there are not too many stations added. But still, engagement of countries to host observation remains important. Or you can try to convince donors, in particular, there are a lot of philanthropies, who can change the game. And for instance, for installing new site in Africa, we got a donation with mainly our US colleagues, like a philanthropic gift, that would allow us to get 5 instruments. And that's very important because if one donor gives 5 instruments, it's 1 million, it's not too much. Another is giving 5 instruments for the Amazon, and so on and so forth. You can build a network with transparent data processing. So I think philanthropies, in particular in the US, have been a very powerful leverage to fund this kind of project. There are some risks because in the US, philanthropies are rich, more rich people. And because I think it's associated to some tax exemption, they have the duty to spend money in the year, which means that they must give cash. In France, we have foundations, but they can keep the money for 10 years. So they will say, write a proposal, we'll see next year. If they have a budget cut, they will postpone the budget. So having both powerful philanthropies and a good regulation that obliges them to spend a significant fraction of their funds every year, I think is very important.
You've played an important role as a convening lead also with the IPCC, the Intergovernmental Panel on Climate Change. Looking forward into the next assessment cycle, is the IPCC, with its 6-7 year wait between reports, is it still fit for purpose? Can it still inform today's policymaking with such a slow pace?
Yeah, I'm a bit concerned that there is maybe a risk of like a bifurcation and fragmentation for IPCC because if you have a slow process, people will do nothing or the assessment will not be completely comprehensive because science is still progressing quickly. The other risk, but I'm not following changes in IPCC very closely, is that governments say, okay, the knowledge basis, we know it, nobody reads it, we only read the summary for policymaker, we trust you for the chapters, so we don't need a carbon chapter. It's a way to say it's not important. We need something about adaptation, what we have to do, and we need specialized report, like a report on cities, a report on the tropics. And this has a fragmentation effect because there is only one climate problem with multiple impacts. And if you start to have a report only on cities, only on cryosphere, permafrost, it will be very useful. But we lose the big picture, which is that CO2 increase is a global problem. Global emissions are changing the climate for everybody. So you need to understand the global carbon cycle and not think that it's a kind of known engine and now we have to look at the consequence.
Are you a bit concerned, because right at this moment there's a bit of a battle going on amongst countries about the timeline of the next IPCC reports, whether they should be before or after the next global stocktake?
Yeah.
And it seems there's a tension which at the moment is not resolved, right?
Yeah, I'm not following this, but yeah, you understand that some countries, they want to delay or to weaken the IPCC, that's very clear. And some countries, they want to have more frequent assessment. And what I'm feeling now is that if it gets too slow, the impact will be much less. Typically, people want information about last year. And one of the reasons for the very highly cited like global budget paper is that it's a yearly product. So every year, at least you have the microphone for one day. You can explain the carbon budget, and it has a very big impact in the media everywhere because it's a yearly product. For other budgets that we produce every 5 years, the impact is 10 times less. And you can see that the IPCC is the same for climate. Like people want to know if 25 was a bit cooler than 24 or not, and they go to the Copernicus website to understand the global temperature. They don't have to wait in 6 years or the IPCC to tell them that 23, 24, 25 have been the warmest years of the century. People want something fast. Typically, there is a big monster or possibly very large El Nino coming in 26. We want to have the answer how it's going to affect the carbon cycle in early 27, not in late 2030. Yeah?
So a decade ago, the world's leaders gathered here in the city for COP21. The outcome was obviously the Paris Agreement. Looking back, knowing what we now know and living with the current geopolitical tensions, what impact do you think that agreement has had? And what comes next for climate action globally?
Yeah, so the agreement has a merit to exist because we had several failures before, like Copenhagen failed because I think countries try to have a normative approach where everyone would have a quota of emission reductions, and this failed. So Paris, in a sense, was weaker because it's just everyone is pledging something, putting cards on the table, and then we take the sum of the cards and we see if the pledges are good or not. So in the beginning, of course, the momentum and the fact that almost all the countries agreed to sign the treaty, it's a very important event. But there are some loopholes. The fact that I would have thought that pledges would be very hardly carved in stone, and they will be followed by implementation policy, and that governments could even be sued if they don't implement their pledges. What we see now is that there is a big gap between what countries promised. If you believe all the promises, we should head maybe to just a little bit more than 2 degrees, not too much. But if you look at the real emission trajectory, we are going to be much warmer than 2 degrees. So there is a difference between the promise and the action. And the difference is increasing over time. We're not taking fast enough action. So that's a big problem. And unfortunately, because Paris was, they don't have mechanism of regulations for countries that don't keep their promise. The gap is widening, and the countries have a rendezvous in 2030. And I'm wondering what will happen. They will say, oh, we have a bigger gap. And they will say it's because there was a war in Iran, it's because there was a COVID, it's because there was some drought and we had to emit more to cool our population, or we wanted economic growth and we couldn't stop increasing carbon emissions. So what I'm afraid of is that we will be in front of a big emission gap in 2030. And countries will have good reasons, because of economic downturns, geopolitical reasons, for explaining that it's not their fault. And also countries have been mainly, some of them, like over-reliant on land carbon sinks. Like typically in Europe, we had forests and they were taking as much carbon as the emissions of the entire Netherlands and Belgium. So, or I think even France and Belgium. So it's a significant absorption. And the European Commission, they opened the Pandora box. They said, well, because reducing industrial emission, it's very hard to get to neutrality. We could get a little bit of help by, putting the forest on board. So, of course, they put the forest on board. The industrial effort becomes less. And now we have seen that the European carbon sink has already decreased because of climate change and bark beetles by 30%. So this is a fact. But what are the countries doing? Well, they do nothing. They say, oh, too bad, our forests are not taking enough carbon. But the consequence is that they want to meet the target. They should say we should do more effort in other sectors, or we should manage the forest in a completely different way. But they witness the problem arriving with collapsing forest carbon sink without any clear action to either readjust the target or take stronger actions. So that's typical examples where there is a gap between what you see happening and what you would need to have for 2 degrees. Huh?
Mm-hmm. I mean, thinking about the Paris mechanism and the kind of the framework of it, do you agree that nations should still self-report their emissions when scientists could now do it with far greater accuracy and in real time using satellites and other measurements?
Well, having self-report means it's a mechanism countries can accept. And we have to be a bit modest on the scientific side because, let's say, satellite promoters have conveyed the idea that satellite can measure emissions. Honestly, it's not possible because satellites are very sensitive to clouds. Imagery is very coarse. Satellites are good to get a good map of the natural carbon sinks. That's fine. But satellites cannot give you accurate emissions for London or Paris or France because they don't observe accurately enough the column of CO2 over big cities. You have a lot of small villages and small towns which are basically invisible from satellites. So everybody has to rely on national reports. Huh? Mm-hmm. The global carbon budget we produce emissions, but they are based on national data. The International Energy Agency is producing their own emissions. It's based on national data. National reports are obviously based on national data. The only thing which differs is the amount of salt and pepper that everybody is putting in the calculation or the gap filling. But right now, for fossil carbon, we still need national energy data. However, for other gases like methane or for natural carbon sinks or sources, yes, scientific data, observations are quite powerful. Mm-hmm. So I still think we need national reports. Maybe the mechanism has to be more transparent, but it's coming. Paris Agreement has a transparency framework. It's good that the scientific community is comparing their own estimations with the national data. But I think it's an error to think that the scientists for fossil CO2 have their own independent observed estimate that they can match against country data. So far, it has not yet happened. Mm-hmm.
With the rise in the use of artificial intelligence and ever smaller research budgets, how do you see the future of the peer review system within academia that kind of underpins all climate science, really?
Yeah, it's like Trump. It's an ongoing experiment that we are all, trying to grasp with improper data. So I feel like your big bibliographic study, we need statistical data and analysis of the impact of AI on the peer-reviewed system. There was a survey published by Nature last year, and they found that everybody who responded is already heavy using AI for reviewing other papers, for writing their own papers, and maybe they don't, say it, they understate their use of AI. And there was another very nice paper in Science where they look at papers writing and publication acceptance rate before and after GPT in a kind of counterfactual models. Exactly what we do for climate science. And they found that after GPT there was an increase, a very sharp increase of the number of publications, but the acceptance rate per publications decreased a lot. So the effect of AI from this single study seems to be that it will facilitate, of course, the proliferation of studies, but because journals have a limited capacity, and also because reviewers are starting to use AI to do their review, the rejection rate will increase a lot. So more studies, but less high impact studies, lower impact, because journals will be flooded by studies of uneven quality. And also, if you delegate to AI the care to review papers, I have seen that. I have submitted papers, and the reviewers, you can see that it has been reviewed by an AI. And the AI is very wet. Basically, the reviewer is prompting, I want to reject this paper, give me some good reason for reject, and you can see what the AI is doing. And it's very difficult to fight against that.
So you suggest there's a kind of, at the moment, there's a bit of a self-correcting mechanism, because even though there might be an increase in the number of papers submitted and reviewed, the ones that actually pass is decreasing, so maybe it balances out. But it sounds like in the future that balance currently might not maintain itself, and you may just see an ever-increasing rise in papers. But presumably, is your concern that they just might be lower quality, or they might be very bland and non-unique?
Yeah, the concern is about non-unicity, because it accelerates things. So you have a proliferation of studies. AI accelerates also the doing of research. Like if you have to analyze data with statistics, before it took months of coding, and now you just ask those generative AI.
But are you fine with that? Are certain,
I'm fine with that.
Certain uses of AI are okay, but some is a red line, and you don't want to see it?
Well, we don't have experience, and it's progressing so fast that right now you could say that papers written by AI, you read them and you see that they don't have a good quality, but maybe tomorrow generative AI will write perfect nature papers, because they are learning so fast. So maybe there will be a decrease in the quality. But
presumably it's the key to science, right, is you can replicate, you can reproduce the findings. So if the AI, the code, or the way the paper was written is effectively a black box, you don't know how the AI did it. Is that key pillar of science that you can reproduce a finding?
Yeah, I think,
is that increasingly eroded?
You're right. I think there is a risk of erosion of reproducibility. On the other hand, it's a double-edged sword, because AI could also make code more transparent. So for me, of course, we need some kind of guidelines to declare if AI was used to write papers, for which reason, in which place of the papers, and if AI was used for reviewing. For me, the big problem is for the review, because if all the review is delegated to AI, it can become very subjective. And then the other problem is that a journal like Nature, every year in a big Nature journal, I think they have room for, 10, 15 climate papers, and they won't increase, still be 10. So if AI makes the doubles or triples the number of input papers, the filter will still be there for very high profile papers, because people can only distillate and read Nature for 10 papers per year, which means that there will be a lot of junk and people disappointed by high profile journals. And maybe some other journals, they will take the opportunity, including Nature and Wiley, they will say, let's open new houses to be able to accept all these papers and the revenue that comes with the papers. So I think we will see a proliferation of papers. High profile will still stay high profiles, and we will see a lot of opening of new papers to accept the flood, the wave of AI-based papers. We are also going to see the future will come also from China, because right now it has been very important for the Chinese community to publish in so-called Western journals like Science, PNAS, Nature. But there is also willingness to have their own Chinese Nature or Chinese Science, and maybe in 10 years we will see, because the production is so high in China, that the most highly cited journals will not be the Nature Climate Change, but will be a Chinese equivalent.
So you can imagine in 5-10 years, Western climate scientists trying to get their new papers published in Chinese language journals.
Not in Chinese language.
But Chinese-based journals. But they would still publish maybe in both languages.
Right. Because it's changing the center of the world. With such a big community, it's very important to have their own journals. Like France in the early century, there are a lot of scientific journals in French which have disappeared. And those journals can get a very big impact factor. And of course, they will become attractive for everyone. I don't think they will replace Nature tomorrow. But all the sub-nature group, like Nature Communication, Nature Climate, Nature Sustainability, could be vulnerable to this rise of, equivalent high-impact papers from China.
Mm-hmm. So you've obviously in your long career been a very prolific author, which is why, you obviously have a high citation, and that's why you appear, right at the top of our own Cosmos database. I think is it right? You've published maybe more than 1,000 studies, or you've been an author on more than 1,000 studies, which over your whole career is like, I don't know, on average, like a paper every 2 weeks or something. That's incredibly prolific.
It seems something is wrong, because some people say, how can you publish a paper every week or 2 weeks? I can say, my computer here, that every 1,000 paper, I made some intellectual contribution. But of course, some papers I write myself. I still write every year 1 or 2 or 3 first author paper, and you have to. It's painful. You have to write, rewrite, do your referencing, and so on, and sometimes do your figures. A lot of papers, there is a positive feedback. If you have a relatively high reputation, people will send you draft of manuscript, and they will ask for your advice, and it takes only a few hours to read and think about.
And then you're added as an author.
And you are added as an author.
The tradition and the procedure is that you get added as an author.
Yes, let's say the normal procedure should be that nobody should be an author without reading the paper or just saying, it looks good. And I make the effort to read through the entire paper and to send comments. But sometimes it's, let's say, being an author is only a few hours of work, maybe 3 to 6 hours. Because the papers are already well structured, and I can still have maybe a marginal contribution. But of course, for the papers that we build here in the group with students, or that I write myself, then it's a completely homemade construction.
And on top of that, you're presumably also reviewing. You're part of the peer review process. You're reviewing other people's papers for journals, something.
Yes, I have to do reviews. And again, if you wanted the system to be sustainable, I can blame myself, because if I publish something like 100 papers per year, I should review 100 papers per year, and I can confess in front of the camera that I'm not doing that. So that's also something that has to be taken into account. If we want the system to continue, people should try to review almost as many papers on average. And I have a big imbalance.
So looking back across that whole career, 1,000+ studies, which single study that you've authored gives you the most satisfaction, or is the most sort of memorable to you across the whole arc of your career?
Well, we are humans, so we look at the past like a golden age. And I was very pleased by the first paper I wrote in Science, because it was the first one, so it's like the first time you do something. It's very nice. Because it was a collective experience, I was the first to have access to this C13 isotope data measured by colleagues from NOAA and University of Colorado. At the time, carbon cycle was not an industry. You had 30 people, and you knew all of them. You knew Dave Killing and Peter Tans and Ines Fung personally. So that was a very stimulating community. And I was very pleased and proud to have been able to do the result. And because I was only a postdoc, I received a lot of help from my supervisor to write the paper. But to see the paper published, I think that was a super terrific experience. And also what was even more rewarding is that we published the paper. And because the community was so small, it was hundreds of people, 30 and maybe 10 influential, I had the opportunity to explain my study to Charles Killing, to Ines Fung, to Martin Hyman, to all these big guys. Now, you just publish and you hope that you will be read, but you go to a conference and there is 5,000 of people who have a carbon cycle session. Huh? So the kind of small size of the community and the fact that everybody was aware of all the research. Some people still had a complete overview of all the carbon papers. It was very stimulating.
Okay, we're almost coming to the end now. I just want to ask maybe a couple of sort of more personal questions. One, which is like, what keeps you up at night when you're thinking about climate change? Is it an area you feel maybe doesn't get enough attention at the moment, for example?
Well, I am feeling I'm a bit obsessed by these missing carbon loss issues, like all these permafrost and abrupt changes. So I think we are living in a gradual change world, and honestly, we should introduce the possibility for abrupt changes in climate models. And something also that worries me, although I'm not really a climate modeler, is the fact that the complexity of the models has become so big that sometimes people don't even know, what was in this part of the code because it has 1,000 of parameters, and the team is only 5 people and 5 postdocs have left and they knew this part of the code. So we also are facing, an increased complexity, and we need to be able to cope with it, either by using AI to accurately emulate or substitute part of the climate models, or finding a way to have the knowledge more traceable, because those are models with thousands or hundreds of thousands of lines of code. Some of them have been developed by a postdoc or PhD student who left 10 years ago, and maybe it has bugs, and there is no, the quality of the code is, I think, not as good because we don't have the same resource and the quality of industrial code. And that's still something that I think people are oriented to discover. So they are going to add something to publish in Nature, but the maintenance and optimization and the traceability of the code is something which is very, very important.
Okay, the final question is, it's one that takes you right back, but even before the beginning of your long career, which is, can you remember the first time you became aware of climate change? Were you at school? Were you an undergraduate? What was it that first triggered your interest in this topic?
Yeah, well, when I did my study, I was in theoretical physics. It was in the late 80s. So nobody was really, I knew no one working on climate science. And the story that I needed to get an internship to validate my master degree. And I was a guy who never cared about this, so I needed to find an internship, and everybody had found one in the physics lab, but they were all filled. And I had a friend in the university, and I told her, can you help me find an internship, because otherwise I won't have my diploma. And he said, well, I found one in a climate lab with Jean Jouzel to work about the ocean, 2 months, and maybe you can ask him if he had space for you. So yes, please, because I did my internship. And I went there, and there I discovered, people like Jean Jouzel, who was just at the beginning of the Antarctic ice core success story. So he was becoming famous, but not yet like a rock star. And it was quite fascinating to understand, like in 87, 88, that people were already working with ocean models, with ocean tracers, with paleoclimate, and even with climate models. because the community was much smaller, it was an interesting time to be in a lab where you have people doing, isotopic measurements and climate models.
Okay, Philippe, thank you very much for talking to Carbon Brief today.
Thank you so much.